Now, we don't need a source to drive an LC circuit if we have resonance. So we'll talk about how that fits in. Okay, so we see here that the voltage of the source has to be Vmax times the cosine of omega t minus 90 degrees. Because cosine of omega t minus 90 degrees is the same as sine omega t, and we want to see how the voltage of the source might or might not be in or out of phase with the voltage of the current. And we see from this that the voltage of the source is 90 degrees from the current voltage. Now, being a little bit funny here, because as I have the current or the circuit, the phasor drawn here, this is negative, but Vmax should be positive. So this Vmax might be negative, and that can get a little bit confusing. If this is negative, then this would be negative Vmax here. The voltage of the source would be negative Vmax times this, which would affect this phase angle, and it would actually then be Vmax times the cosine of omega t plus 90 degrees. So I'm going to kind of fix that by saying that's either plus or minus 90 degrees, and in analyzing the circuit, you would be able to figure out whether it's plus or minus. Okay, meaning that the source will be out of phase with the current by 90 degrees. Whether it's 90 degrees ahead or 90 degrees behind depends on whether this quantity is positive or negative. Okay. Now, the other thing we want to talk about before we get to the phasor for the LRC is simply that if your VC and your VT are equal and opposite vectors, if the magnitudes of these vectors are equal and opposite, what's that mean? That means the voltage of the source, well, this is zero. That means you have zero source voltage. So, and if you have zero source voltage, then you have an independent oscillation. You don't need a source in there. Now, you got to get rid of the resistor. That's just so you have an LC circuit. Okay? And then you can charge up your capacitor and remove your source and your resistor, of course, and then this current just drives itself, to the extent that it's an ideal current with no resistance. Naturally, these wires all have resistance, so even if you got a good superconductor, you're still going to lose energy eventually. But this circuit can keep going for a long time if you have a good superconductor to conduct it. Okay, good superconductors throughout, including in the coil. All right. And then if you drive the circuit with a source that's that's at the same frequency as the natural frequency, you're going to get well, in the solution to your differential equation, you're going to get a slightly different solution here. That's where you're going to get a t times your cosine of omega t. That's going to increase the amplitude of your resonant of your voltage or your current in a linear fashion. So we saw that previously. We saw how that comes out of the differential equation. Okay, that's all I'm going to say about the LC case. Now we want to go to the case where we do have a resistor in here, so we can talk about the LRC case.